This is the second video over L'Hopital's rule. In the first video, we looked at the two basic indeterminate forms. Let's remind ourselves of what the two basic indeterminate forms are. Our two basic indeterminate forms are 0 over 0 and infinity over infinity. These are forms that cannot be determined to have a definite value in all cases. The two that we can apply L'Hopital's rule to are the basic forms 0 over 0 and infinity over infinity. In this video, we're going to look at two new forms in black, 0 times infinity and infinity minus infinity. I need to make that a little bit longer of a minus sign. The problem with 0 times infinity and infinity minus infinity is we have a basic tug-of-war going on. It turns out that not all infinities are the same size. Some infinities are larger than others. For example, the number of counting numbers is what we call a countably infinite set. The number of rational numbers is also countable. However, the number of irrational numbers and the number of real numbers are an uncountable set, meaning that they are a size of infinity larger than the counting numbers or the rational numbers. If you have infinity minus infinity, then the problem is, which is the larger infinity, or are they roughly the same size? If they're roughly the same size of infinity, then infinity minus infinity, this great tug-of-war, could grind to a stop at any finite real number. This is why it's indeterminate. We have a similar problem with 0 times infinity. 0 times any number tends to want to make it 0. But in infinity times a number tends to want to make it huge. So who's going to win this tug-of-war? 0 or infinity? Both of these need to be converted to one of the two basic indeterminate forms, 0 over 0 or infinity over infinity, before you can apply L'Hopital's rule. Let's take a look at an example and see how to apply it. In example 1, we have the limit as x approaches infinity of x squared times e to the negative x power. When looking at this, in order to determine what kind of limit we have, we will do what we always do, which is plug in what the limit is approaching, in this case infinity, in place of the variables x. It seems strange to plug in infinity since it's not a number, but we have to, in a sense, visualize what's happening to the graph. You can think about infinity squared becoming infinity, or e to the minus 0, as 1 over e to the infinity, or e to the minus infinity. Or you can think about what the graph of x squared and e to the minus x look like. The graph of x squared is a parabola. As x goes to positive infinity, the y value goes to infinity. That gives us infinity for the first one. The graph of e to the negative x, which is second, is the graph that comes down and approaches the x-axis as an asymptote. As x goes to positive infinity, the graph of e to the minus x goes to 0. This gives us infinity times 0, one of the two arithmetic indeterminate forms. Arithmetic meaning arithmetic, subtraction and multiplication in this case. They're not basic forms because they're not 0 over 0 or infinity divided by infinity. However, we can rewrite them in that form by converting this current product into a fraction. The simplest thing to do is to take the one with the negative exponent and drop it to the denominator. This will give us the limit as x approaches infinity of x squared divided by e to the x. Notice I have not put in the notation for L'Hopital's rule because I have not applied L'Hopital's rule yet. All I did was algebraically drop the e to the negative x to the denominator, making the power a positive x. Now I need to evaluate again what the form is. As I plug infinity in, x squared goes to, yes, infinity. E to the x has a graph that looks like the exponential, which as x goes to the right goes to positive infinity. Now I have infinity over infinity. Since this is one of the two basic indeterminate forms, I can now apply L'Hopital's rule if the two functions are differentiable. I know that x squared is differentiable everywhere, and so is e to the x. Thus, I can apply L'Hopital's rule. This means that I can take the derivative of just the numerator and divide by the derivative of just the denominator. The derivative of x squared is 2x, and the derivative of e to the x is e to the x. When I look at this, again, now I have a line over an exponential, which again has the form of infinity over infinity. This means I can do L'Hopital's rule again, since they are both differentiable functions. Applying L'Hopital's rule one more time, I come to 2 for the numerator and again e to the x for the denominator. 2 is a constant, but the denominator is getting larger and larger. A constant divided by infinity gets driven down to 0. So the value of this limit is 0. Let's take a look at another example. In example 2, you'll see that I have the limit as x approaches infinity of x times the sine of 1 over x. On the right, I've written down the two basic forms, 0 over 0 and infinity over infinity. Remember that without one of the two basic forms, I cannot apply L'Hopital's rule. I also cannot apply L'Hopital's rule unless the numerator and denominator functions are differentiable near whatever value the limit is approaching, in this case, positive infinity. Note that I do not currently have a fraction. Although there's a fraction in the argument to the trig function, the basic function is x times sine, which is not a fraction. Both basic forms are fractions in nature, which means before you can do L'Hopital's rule, you must always have a fraction. This means that if it is something I can use L'Hopital's rule on, it is not ready for L'Hopital's rule. Let's plug in infinity and see what we get for our format. Plugging infinity for x, I get infinity times the sine of 1 divided by infinity. A constant divided by infinity goes to 0. We can indicate that with a diagonal arrow and a 0 at the end of the arrow. The sine of 0 is 0, which means this has the form of 0 times infinity, or infinity times 0. Since I'm looking at this, this means that I could do L'Hopital's rule if I can get it in a form where the numerator function and the denominator function are differentiable at infinity. In this case, I do not want to move sine because sine is one of the basic trig functions that I understand pretty well. If it were cosecant, I would move it to the denominator and write it as sine. If I'm not moving sine, then I have to move x. Note that I cannot separate the argument to the trig function from the trig function itself. This means that what I'm going to do is an algebraic manipulation where I divide by the reciprocal of one of the factors. Since I'm leaving sine of 1 over x in the numerator, I need to divide by the reciprocal of x, which is 1 over x. Remember that the bottom of the bottom, or denominator of the denominator, is actually the numerator, and this would give us back what we started with. Now, however, I can see clearly that I do have a fraction. Now I'm going to plug in again to see whether or not this time I get one of the two basic forms. The sine of 1 over x, when I plug in infinity for x, is again going to become 0. In the denominator, I have 1 over infinity, but a constant divided by infinity gives me 0 over 0. This is one of the two basic indeterminate forms, so I can do L'Hopital's rule. I indicate that with the L'H over the equals, and I take the derivative of just the numerator by itself and just the denominator by itself. The derivative of sine is cosine, frees the inside function, times the derivative of the inside, which is 1 over x. To take the derivative of 1 over x, I'm going to think of it instead as x to the minus 1. Since I have 1 over x in the denominator as well, I'm going to indicate that by writing the x to the minus 1. Now, in order to do this, I can simply use the power rule. Using the power rule, this leads me to the limit as x goes to infinity. In the denominator, I get a negative 1 x to the negative 2. This gives me the cosine of 1 over x in the numerator times, in parentheses, negative 1 x to the minus 2, also in the numerator. Notice that because these are identical, I should be allowed to cancel them out. This will lead me to the final limit as x goes to infinity of the cosine of 1 over x. Now when I plug infinity in place of the variable x, 1 over infinity goes to 0. When that goes to 0, that means that I get the cosine of 0, which is 1. Thus, the value of the original limit is 1. Let's take a look at another example of the arithmetic form. In example 3, we see one with the indeterminate form infinity minus infinity, which we have not done yet. When you look at this one, realize that when you plug in infinity for x, you do get infinity. Plugging in infinity in place of the x here gives me also infinity. In other words, both of those graphs, as I go to positive infinity, go to positive infinity. Infinity minus infinity is a tug of war. It's not clear which is the larger infinity, or if they're the same size, on what finite real number it'll grind to a stop. In the chapter 2, when we solved these, we multiplied the numerator and the denominator by the conjugate. Multiplying the numerator and denominator by the conjugate gave us a way to algebraically manipulate it to try to get some cancellation. In this case, we don't necessarily want to do that, but we do need to have one of those two basic indeterminate forms. Our basic forms, again, which I will be repeating over and over again, are 0 over 0 and infinity divided by infinity. If you don't have one of those two, you cannot apply L'Hopital's rule. First, note that x minus the square root of x squared plus 1 is not a fraction. One of the easiest things to do to convert something that is the difference of two terms into a fraction is to multiply it by a form of 1. In this case, I'm going to multiply it by a form of 1, which consists of 1 over x over 1 over x. I'm going to multiply this by 1 over x over 1 over x. Again, since I'm going to infinity, I know that the x value is very far from 0, so 1 over x is defined. Anything divided by itself then, provided it's not 0, is just the number 1. So I am allowed to do this. You could also multiply by 1 over x squared over 1 over x squared. Any fraction of this form should work. When I complete this, this is going to give me a new version of the limit, which is going to look like x approaching infinity of x minus the square root of x squared plus 1 over x, all divided by 1 over x. Now when I'm looking at this and I'm trying to determine what's going to happen, I need to do some simplification. If I'm going to do some simplification, what's going to happen? How can I simplify what's in the numerator? Remember that since x is approaching positive infinity, at some point all the values are positive. In that case, the square root of x squared, which is normally the absolute value of x, will equal x as x goes to positive infinity, and negative x as x goes to negative infinity. Since we're going to positive infinity, I know that the square root of x squared will be x. This means that I can rewrite this denominator x underneath the radical by rewriting it as the square root of x squared. First, however, I'll split the numerator into two pieces. In this case, this will lead me to the following line. This gives me the limit as x approaches infinity of x divided by x minus the square root of x squared plus 1 divided by, and instead of writing the x under the radical, I will write it as the square root of x squared, since it is x as x goes to infinity, all divided by 1 over x. Now when I simplify this a little bit, I get the following. Oops. This will give me the limit as x goes to infinity of 1 minus, since I have two radicals, I can move them together under one radical, and I get x squared divided by x squared plus 1 divided by x squared, all divided by 1 over x. Now I'm ready to plug in again. X squared divided by x squared will of course reduce to 1. This gives me the limit as x is going to infinity of 1 minus the square root of 1 minus or plus 1 over x squared, all divided by 1 over x. Plugging in, I get 1 minus the square root of 1 plus 1 over infinity. When I plug in infinity for x, infinity squared is still infinity, divided by 1 over infinity. 1 over infinity goes to 0, so I get 1 minus the square root of 1 over 0. But 1 minus the square root of 1 is also 0, so I do have an indeterminate form. That means I can now apply L'Hopital's rule. If I apply L'Hopital's rule, I should be able to simplify this and see what I get. Let's take a moment to do that. Turn off the video, take L'Hopital's rule, and turn the video back on to check and see if you got what I got. When you applied L'Hopital's rule, remember that you must do the chain rule for the interior part of this radical. The derivative of 1 is 0, so you end up with, and I think I've lost a negative. This should have had another negative here for this negative. 1 over 2 the radical times the derivative of the inside. The derivative of 1 over x squared is negative 2 over x cubed. Then the derivative of 1 over x is negative 1 over x squared. These negatives will cancel. These 2's will cancel. This will leave me with another negative here. The x cubed stays in the denominator. The 2's cancel, the radical is still in the denominator, and the reciprocal of the denominator becomes the product. This will give me another negative here and here, but note that the x squared and x cubed cancel, and I get an x on bottom. When I plug in infinity again, 1 over infinity squared goes to 0, so I get the square root of 1. However, the x also has infinity plugged in, so I get a negative 1 over infinity, which goes to 0. It is not as often to find the infinity minus infinity form, but on occasion we will see it, and you need to know how to handle it. The rule of thumb is to convert it into a fraction by multiplying by some form of 1. If you have a trig function, you may want to write them in terms of sine and cosine and get a common denominator. You must have a fraction to get a basic form. Those are the two arithmetic forms. There are 3 additional forms. Let's take a quick look at the 3 power forms for L'Hopital's rule. There are 3 indeterminate forms that are powers. There are 2 basic forms, 0 over 0 and infinity over infinity, 2 arithmetic forms, 0 times infinity and infinity minus infinity, which represent colossal tug-of-wars, and 3 power forms. Here are the 3 indeterminate power forms. The first 2 have a logical reason, which is 0 to the 0 and infinity to the 0. These 2 power forms have a reason that they are indeterminate that is easy to understand. The final one is not easy to understand. It is 1 to the infinity. It doesn't seem to make sense, but 0 times itself infinitely often is still 0. Unfortunately, 1 times itself infinitely often is not necessarily 1. In other words, if you have any magnitude at all, multiplying it by itself an infinite number of times can cause something bizarre to happen. What about the 0 forms? 0 to the 0 and infinity to the 0. Why are these considered indeterminate? You have to remember where the 0 power rule came from. If we take a simple number like 4 squared and divide it by 4 squared, you know that this is 16 divided by 16, which must be equal to the number 1. However, if you think of it in its power rule form, we take, because the bases are the same, we take the powers and subtract. And it is always numerator power minus denominator power. And this gives us that it's also 4 to the 0. In order to make this work, we must define anything to the 0th power to be 1. This is why 0 to the 0 is indeterminate, because 0 to the 0 would imply that we had something like 0 to the first divided by 0 to the first, which would be 0 to the 1 minus 1, or 0 to the 0. But 0 divided by 0 is undefined, which means that in the limit form, it is indeterminate. Also, note that 0 divided by 0 is one of our two basic forms. If you look at infinity to the 0, you also have a basic form. Infinity to the first divided by infinity to the first would also, using the power rule, lead to infinity to the 0. But we know that infinity divided by infinity is also a basic form. That means that it is indeterminate. The 3 power rule forms for L'Hopital's rule are far more difficult to apply than the previous 4. These last 3 have their own videos to deal with just those forms. Let's look at a separate handout called Indeterminate Forms that you can find in D2L in my folder under L'Hopital's rule that will help us to summarize what the indeterminate forms are and what some of the other limits are. Let's take a look at that now. Just to remind you, here are the 7 indeterminate forms for evaluating limits. 0 divided by 0 and infinity divided by infinity are the 2 basic forms. There are 2 algebraic forms representing a tug-of-war, 0 times infinity and infinity minus infinity. There are 3 power forms, 0 to the 0th power, 1 to the infinite power, or infinity to the 0th power. L'Hopital's rule can be used to find limits that result in an indeterminate form, provided that the function in the numerator and the function in the denominator are differentiable. Since most of our functions are differentiable, this is not a serious limitation. Let's take a look now at some of the ones that are not indeterminate. The not indeterminate forms come in 2 basic types. First, what about the ones where the limit does exist? If you have 0 divided by infinity of any power, then this has the limit of 0. In other words, the limit exists and it is the finite real number 0. Also, if you have the form 0 to the infinite power, or 0 times itself infinitely often, this is not indeterminate. We know that this has a limit also of 0. The third one is any constant, no matter how large or small, divided by any form of infinity, positive or negative, has the limit of 0. You can also have limits where you plug in for x or do some kind of algebraic manipulation in order to evaluate. In these cases, the limit does exist when it is a finite real number. What about the other types of limits that are not indeterminate? The other types of limits that are not indeterminate means that they are not approaching a finite real number, but they do not exist because they approach infinity or negative infinity. What kinds of forms might you get that would lead to a resulting limit of infinity or negative infinity? Infinity divided by 0 will go to either infinity or negative infinity, depending on which infinity it's approaching and which side of 0 it's approaching from. So for example, let's look at this one here. When we're looking at this one, we have positive infinity divided by approaching 0 from the left, meaning from numbers that are to the left of 0 or negatives. A positive divided by a negative would indicate it goes to negative infinity. If I'm approaching positive infinity in the numerator and I'm approaching 0 from the right in the denominator, then this will also go to infinity, but it will be positive infinity. Approaching negative infinity and approaching 0 from the left, the negative side, will lead me to positive infinity, but approaching negative infinity and 0 from the right will lead to negative infinity. There are some other values as well. Let's take a look at some of the others. What is infinity times infinity? Well, they agree. Let's go to infinity. What about negative infinity times negative infinity? Let's go to positive infinity. Woo! Off they go. Negative infinity times infinity, negative infinity, not a problem. The addition ones and subtraction are a little bit more problematic, but again, they're pretty basic. Infinity plus positive infinity, they both want to go to the right, so they go to the right. Negative infinity plus negative infinity, this one wants to go to the left, this wants to go to the left, so they go to the left. The third one is a little bit confusing because of the double negative, but this is positive infinity minus a negative infinity. The double negative makes this positive infinity, which makes it more like the first one. So again, they go to positive infinity. The indeterminate form, remember, is when they don't agree. This one wants to go to the right, this one wants to go to the left. That's a tug of war. The next cases that we need to look at that are not indeterminate are the constant divided by 0. When the top is a constant and the bottom is getting smaller and smaller and approaching 0, what we get will either be infinity or negative infinity, depending on whether the constant's positive and whether we're on the right side, the positive side of 0, or the left side, the negative side of 0. Remember that in all cases, these represent limit values, not actual numbers. This is what the limit is approaching. We cannot have a real number where we actually divide by 0. This is the limit, not the actual number. This is the end of this video, which covers the 2 arithmetic forms and introduces the 3 power forms. There will be other videos that deal with just the power forms.